Dear students, last time we have seen some theoretical details of distribution law. Let us see today applications of distribution law. Distribution law has numerous applications in physical chemistry. Let us see important applications of distribution law here. As per important applications of distribution law are concerned, the important applications of distribution law are solvent extraction, study of complex ion or determination of equilibrium constant of a chemical reaction using partition coefficient. Third important application of distribution law is partition chromatography or liquid-liquid chromatography. Fourth important application of distribution law is determination of molecular state of solute, or in other words, determination of association of solute in a given solvent. Fifth important application of distribution law is determination of solubility of solute, and the sixth important application of distribution law is determination of dissociation constant. So these are the some important applications of distribution law. With this, let us see the first and the most important application of distribution law. And the first and most important application of distribution law is solvent extraction. Let us see at first what is solvent extraction. Solvent extraction is a versatile separation technique used for separation of many organic compounds, inorganic compounds, using suitable solvents known as extracting solvents, and the extracting solvents which are used for extracting most of the organic compounds are ether, carbon tetrachloride, carbon disulfide, benzene, chloroform, etc. So let us see at first what is meaning of solvent extraction, or what is solvent extraction itself. Solvent extraction is sometimes also known as liquid-liquid extraction. Liquid extraction. Why solvent extraction is known as liquid-liquid extraction? Let us see it at first. In this case, when we want to separate a substance under examination present either in large quantity or present in a very small quantity in an aqueous solution, the solute under examination in given aqueous solution is removed, is taken out using some immiscible solvent with the aqueous solution, and this process, the process of removal of desired substance, desired solute in a given aqueous solution using some suitable immiscible solvent is known as solvent extraction. As here both the solution in which desired solute is present and the extracting solvent used for removing maximum amount of solute present in aqueous solution is in liquid state. Hence this technique is sometimes also known as liquid extraction. With this, I hope you have understood what is solid extraction or liquid extraction. We can define solid extraction or liquid extraction in simple way. As we have seen, this is a separation process. This is a separation technique, a very versatile separation technique used for separation of very large quantities of substances present in given solution, either single or in the form of mixtures with some other substances, or we can separate a very small quantity of desired substance present in an aqueous solution using extracting solvent. So let us see how can we define solid extraction or liquid extraction at first. The process of extracting solute present in an aqueous solution using some suitable immiscible solvent such as ether, carbon tetrachloride, carbon disulfide, benzene, chloroform, etc. is known as solid extraction or liquid extraction. The meaning of word extraction itself indicates that extraction, taking out, this process, the process of solid extraction involves the removal of or the moving of the solute present in one phase into another phase, and the process of separation is carried out simply using separating funnel or separatory funnel. With this, let us see what are the essential conditions for effective solid extraction. The essential conditions for solid extraction are: number one, the partition coefficient of solute which is to be separated, which is to be extracted in a given aqueous solution must be greater and in favor of extracting solvent. So this is what the first and most important condition or essential condition for solid extraction of any desired solute present in a given aqueous solution. Unless and until the partition coefficient or distribution coefficient of given solute is greater and in favor of the extracting solvent, we cannot remove, we cannot extract the maximum amount of desired solute present in a given aqueous solution. So, when we have to separate, when we have to extract any solute in a given aqueous solution using extracting solvent, at that time we have to check the partition coefficient or distribution coefficient of that particular solute in between the water and the extracting solvent which we have chosen. So this is what the first and most important condition for effective solvent extraction of any solute in a given solution. The next important condition or the requisite of solvent extraction of any solute is we must not use whole extracting solvent for extracting desired solute in a single extraction. Instead of using whole extracting solvent for extracting desired solute in a given aqueous solution, if we use portions of that whole extracting solvent and extract the desired solute present in a given solution, we will find that the efficiency of extraction in latter case is greater than the first case. So with this, I am sure you have understood what is solvent extraction or liquid-liquid extraction and what are essential conditions for effective solvent extraction of solute under examination. With this, let me give you few examples of solvent extraction carried out for separation of organic mixtures in academic laboratories like us. As far as separation of organic mixtures is concerned, we will see that we can separate a mixture of benzoic acid and oxalic acid using water and ether. How? We know benzoic acid and oxalic acid, these two organic acids, when we add these two organic acids in water, oxalic acid readily goes into the solution and benzoic acid also dissolves in water, and we get a mixture of both benzoic acid and oxalic acid. So when a mixture of benzoic acid and oxalic acid in water is mixed with ether and the resulting mixture is taken in a separating funnel and second well, we will find that almost all benzoic acid goes into ether, and in this way the separation of benzoic acid from oxalic acid occurs. So this is what the simple example of solvent extraction, or how we can separate one substance from another substance by solvent extraction method. With this, let us switch over to theoretical part of solvent extraction. we know the efficiency of, or rather the magnitude of solvent extraction depends upon the amount of solute extracted in a particular solvent extraction operation. In simple words, the amount of solute extracted or the amount of solute remaining unextracted in a particular operation. Of course, as far as solvent extraction operation is concerned, is very important as per the efficiency of solvent extraction is concerned. In this case, the efficiency of solvent extraction will be definitely higher when the amount of solute remaining unextracted is very small, very less. Isn't it? And therefore, as per theoretical details are concerned, as per theory of solvent extraction is concerned, we have to derive an expression for amount of solute remaining unextracted after extraction. So let us see how can we derive an expression for amount of solute remaining unextracted after solvent extraction. As I have told you, solvent extraction is efficient when we carry out multiple extractions using small volume of extracting solvent. So let us see here at first an expression for amount of solute remaining unextracted after a definite number of extractions, say n number of extractions. Let us suppose we have V ml of aqueous solution and in which certain solute X is dissolved and the amount of solute present in V ml of aqueous solution is W, and the V ml of solution containing W grams of solute is taken in a separating funnel and mixed with small V ml extracting solvent. So let me write it here. Let volume of aqueous solution containing solute is capital V ml. Similarly, volume of extracting solvent or here organic solvent is small v ml. We have assumed here the amount of solute present in V ml aqueous solution and the amount of solute present initially in capital V ml solution is, let us suppose, capital W. Let us suppose we have extracted capital VML aqueous solution containing W grams of solute in it using small v ml organic solvent exclusively immiscible with the aqueous solution, taking in a separating funnel and seeking it well. Let us suppose we have determined the amount of solute extracted, the amount of solute removed from aqueous layer, or the amount of solute remains unextracted in aqueous solution. Let us suppose the amount of solute remaining unextracted is W1 gram. Amount of solute remaining unextracted is W1 gram. When we look at all these quantities, the volume of aqueous solution, the volume of extracting solvent, the amount of solute present initially in aqueous solution, and the amount of solute remaining unextracted after extraction, we can find out very easily the concentration of solute in aqueous solution or aqueous layer and in organic layer. How? Let us see here. Let us suppose concentration of solute in aqueous solution after extraction is C1. What is C1? Here C1 is concentration of solute remaining unextracted after first extraction, Okay, let us suppose C1 is concentration of solute remaining unextracted after first extraction. How much it will be? It will be equal to W1 upon capital V grams per ml. Because what is W1? The amount of solute remaining unextracted after first extraction. And what is capital V? The volume of aqueous solution. So the concentration of solute remaining unextracted after first extraction will be equal to W1 upon V. So we can write it here. C1 is equal to W1 upon capital V grams per ml. Let us calculate the concentration of solute extracted after first extraction. How? We know here the amount of solute present initially in aqueous solution, and the initial amount of solute present in aqueous solution is capital W or W. And we have seen the amount of solute remaining unextracted after first extraction is W1. So obviously the amount of solute extracted in this case will be equal to W minus W1, and that much amount of solute will be present in the extracting solvent. And what is volume of extracting solvent? Small v. So what would be the concentration of solute extracted? Let us suppose the concentration of, let C2 is concentration of solute extracted after first extraction, and obviously C2 will be equal to W minus W1 upon small v grams per ml. I am sure you understood how we have determined C1 and C2. C1, the concentration of solute remaining unextracted after first extraction. In other words, the concentration of solute in aqueous layer after first extraction. And here C2 indicates the amount of solute in organic layer after first extraction. So we know now both the concentration of solute in aqueous layer and the concentration of solute in organic layer. Let us apply distribution law to this. So when we apply distribution law, to this, we get, what is distribution law? Let us apply normal distribution law here, and the expression for normal distribution law is here C1 upon C2. So K is equal to C1 upon C2. What is C1? The concentration of solute in aqueous layer after first extraction. What is C2? The concentration of solute in organic layer after first extraction. Let us substitute the values of C1 and C2 from this. Let us suppose this is expression number 1, this is equation number 2. So let us substitute. C1 is equal to W1 upon capital V. W1 upon capital V, and C2 is equal to W minus W1 upon small v in this expression. So K will be equal to W1 upon capital V divided by W minus W1 upon small v. Okay, let us simplify this. So this will be equal to W1 upon V into small v divided by W minus W1. Let us suppose this is equation number 3. So what we got? We got K is equal to W1 upon capital V into small v divided by W minus W1. Let us simplify it further. On simplification, we get, how can we simplify? We can simplify very easily. So on simplification, we get KV into W minus W1 is equal to W1 into small v. W1 into small v. Or let us simplify it further. KV into capital W minus KV into W1 is equal to W1 into small v. Let us take common terms. As far as W1 is concerned, on one side we get KV W is equal to W1 into small v plus KV into W1. This term, this second term on LHS of this equation, KV into W1 will go in that side, and we get KV W is equal to W1 small v plus KV into W1. Let us take W1 common from RHS of this equation and rearrange this expression for W1. What we get? KVW is equal to W1 in bracket KV plus small v. I can write it like this. Instead of writing small v plus KV, I can write it like this: W1 into KV plus small v. And let us rearrange this expression for what? Let us suppose this is expression number 5. Let us rearrange this expression for W1. So W1 will be equal to KV W upon KV plus small v. When we look at this expression, we will see that what is W1? The amount of solute remaining unextracted after first extraction. What is K? Partition coefficient of solute between solvent 1 and solvent 2. What is capital V? The volume of aqueous solution or the volume of aqueous layer. What is capital W? The amount of solute present initially in given aqueous solution. What is small v? The volume of organic solvent used for extraction, used for extracting the amount of solute present in given aqueous solution. Let us write this equation like this: W1 is equal to W into KV upon KV plus small v. Let us suppose this is equation number, so this is equation number 6 and this is equation number 7. So when we look at equation number 7, we'll see that the amount of solute remaining unextracted after first extraction will be equal to W into this term KV upon KV plus V. Okay, so in this way we have seen how we have derived an expression for amount of solute remaining unextracted after first extraction. Okay, let us suppose we have continued extraction of solute remaining unextracted in capital V ml aqueous layer using another fresh small VML extracting solvent and carried out second extraction under identical conditions. Under identical conditions means what? Let us suppose in this case we have carried out first extraction at 298 Kelvin, that is 25 degrees centigrade. We have carried out second extraction also at same temperature 298 Kelvin. Let us suppose the amount of solute remaining unextracted after second extraction is W2. Amount of solute remaining unextracted after second extraction is W2 gram. Okay. So, what would be the amount of solute extracted after second extraction, or the amount of solute extracted in second extraction? What is initial amount of solute present in aqueous solution? Here, the initial amount of solute present in aqueous solution is W1 gram. And once we understood this, what the initial amount of solute in aqueous solution when we begin second extraction using small VML extracting solvent, we can very easily calculate what the concentrations of solute in aqueous solution and organic solution, or rather aqueous layer and organic layer after second extraction. So here let us suppose the concentration of solute, again let us use same notations here for expressing the concentration of solute remaining unextracted after second extraction and the concentration of solute extracted after second extraction. Let us suppose C1 represents the concentration of solute remaining unextracted after second extraction, and C1 will be equal to W2 upon capital V grams per ml, and C2 will be equal to W1 minus W2 upon small v grams per ml. I am sure you understood how we have got this. C1 is equal to W2 upon V, and C2 is equal to W1 minus W2 upon small v. Okay, because in second extraction the amount of solute initially at the beginning of second extraction present in aqueous solution was W1, and the amount of solute remaining unextracted after second extraction is W2. So obviously the difference between these two, W1 minus W2, will be what? The amount of solute extracted after second extraction. And obviously this much amount of solute will be present in organic layer after second extraction. So, in short, the concentration of solute after second extraction in aqueous solution is aqueous phase is W2 upon capital V grams per ml, and the concentration of solute in organic layer is W1 minus W2 upon small v grams per ml. Let us apply normal Gauss distribution law to this distribution. We get K is equal to, K is equal to C1 upon C2. Let us substitute. C1 is equal to W2 upon capital V divided by W1 minus W2 upon small v. So K is equal to W2 upon capital V divided by W1 minus W2. And here we'll find that when we solve this, we get an expression very similar to that of expression number 7. So the expression which we get in this case for W2, the expression for W2 will be equal to W1 into Kv upon Kv plus small v. Okay, so you can do this very easily. How? Simplify this expression. When we simplify this expression, what we get? Let me simplify it here. Okay. K is equal to W2 upon V divided by W1 minus W2 upon small v. So K will be equal to W2 upon capital V into small v divided by W1 minus W2. Let us simplify this. When we simplify this, Kv into W1 minus W2 will be equal to W2 into small v. So when we further simplify W1 minus Kv W2 is equal to W2 into small v. Let us take the terms containing W2 on one side. Okay, so we get Kv W1 will be equal to Kv W2 plus W2 into small v. Let us take W2 common from RHS and rearrange this expression. So let us write it here. W1 is equal to W2 in bracket Kv plus small v. Let us rearrange this expression for W2, and when we rearrange this expression for W2, W2 will be equal to Kv W1 upon Kv plus small v, and we can write this expression here like this. W2 is equal to W1 into W2 is equal to W1 into Kv upon Kv plus V. So in this way, we have seen how can we derive an expression for amount of solute remaining unextracted after second extraction. Okay, so with this, let us suppose we have continued solid extraction, the extraction process using aqueous layer containing amount of solute remaining unextracted after second extraction. and a fresh small VML organic solvent for third time. So we find that the expression for W3 will be equal to W2 into KV upon KV plus small v, where W3 represents amount of solute remaining unextracted after third extraction, W2 the amount of solute present initially in aqueous solution in third extraction, and K is partition coefficient, V, that is capital V, volume of aqueous solution, aqueous layer, small v, volume of organic solvent, the volume of extracting solvent used for extracting the solute. Let us suppose we have carried out fourth extraction. The expression for amount of solute remaining unextracted after fourth extraction will be equal to W4 will be equal to W3 into KV upon KV plus small v. Okay. This is okay. You can number these expressions. Okay. So let us suppose we have carried out the extraction of solute remaining unextracted after each extraction, and we have carried out the extraction of solute remaining unextracted after each extraction for a definite number of times, and the definite number of times is, let us suppose, n. So in other words, we have carried out this process, the process of extraction of solute under examination for n number of times, and here the n represents what? The number of extractions. Okay, so obviously the amount of solute remaining unextracted after n extractions will be equal to Wn, and Wn will be equal to what? Wn will be equal to W into KV upon KV plus small v to the power n. Okay. Now, how this is so? Let me explain how we got this expression. Let us go back to the expression for amount of solute remaining unextracted after first extraction, and the expression for amount of solute remaining unextracted for first extraction is W1. W1 is equal to W into KV upon KV plus small v. Okay. We have seen how we have got an expression for amount of solute remaining unextracted after second extraction. We have derived that expression. So the amount of solute remaining unextracted after second extraction is W2 is equal to W1 into KV upon KV plus small v. Okay. So let us suppose this is expression number 1, this is expression number 2. Let us substitute W1 is equal to W into KV upon KV plus V in expression number 2. What we get? W2 will be equal to W into KV upon KV plus small v into this KV upon KV plus small v. So this Kv plus small v into this Kv upon Kv plus small v becomes Kv upon Kv plus v square, and final expression will be W2 will be equal to W into Kv upon Kv plus small v to the power 2. Okay, so in this way we have seen W2 will be equal to W into Kv upon Kv plus small v to the power 2. So here, what is W2? The amount of solute remaining unextracted after second extraction. What is W? Initial amount of solute present in given aqueous solution in first extraction. K, partition coefficient, V, capital V, volume of aqueous solution, small v, volume of organic solvent. So in this way, let us suppose we have carried out the extraction of given solute present in a aqueous solution for n number of times. Obviously, the amount of solute remaining unextracted after n extractions will be equal to Wn, and Wn will be equal to capital W into Kv upon Kv plus V to the power n. So, this expression is very important. This expression gives us what? The amount of solute remaining unextracted after n number of extractions. Now, when we look at this expression, we will see that the Wn, the numerical value of Wn, the amount of solute remaining unextracted after n extractions, depends upon what? This multiplication factor, because this W is constant. Initial amount of solute which is to be extracted using some suitable organic solvent is constant, but only this factor, multiplication factor, we can say that multiplication factor decides the amount of Wn. So when we look at this multiplication factor, we'll see that in numerator Kv and in denominator Kv plus small v. So obviously this multiplication factor is always less than 1, because numerator Kv is less than Kv plus small v. So obviously this factor is always less than 1, and the efficiency of extraction depends upon the value of n. How? We know when n is higher, the numerical value of n is higher and higher, obviously this factor, multiplication factor, will be lower and lower, and when it is lower and lower, obviously the product of W into this multiplication factor will be lower. In other words, the amount of solute remaining unextracted after n extractions will be very, very less when we carry out large number of extractions using small volume of organic solvent. So with this, I hope you understood what is solid extraction, what are essential conditions for solid extraction, and how can we derive an expression for amount of solute remaining unextracted after n extractions. With this, I stop here. Next time we'll see few more applications of distribution law. Thank you very much.